if you have a phasor exponential minus j kx, the question is, does that represent a wave that's traveling towards plus infinity, an outgoing wave, or rather a wave that's traveling towards minus infinity, an incoming wave? So as usual, pause the video and try to answer that question. In order to be able to answer that question, we obviously need to move back from the frequency domain to the time domain. So we need to convert our phasor back into something that has an explicit time dependence. So our phasor is exponential minus j kx. And the way we're going to translate that back to the time domain, obviously, is to take our phasor, multiply it by exponential j omega t, which is the convention we use for time dependence. And then we're going to take the real part of that equation. And that will bring us to cosine omega t minus kx. So this is the wave. This is how it behaves as a function of time and also spatial coordinates. So if we focus on what this wave looks like as a function of position, it's obviously a cosine. So wavy behavior like this. And then the question is, what happens if we focus on a specific fixed point on that wave pattern? So let's say we focus on, for example, this point over here, and we want to track what happens to that point as time evolves. Will it move towards the left or will it move towards the right? So how can we express that mathematically? The fact that we're looking at a single fixed point on our wave pattern here. Well, the way we're going to do that is saying that we look at fixed arguments of our cosine here. So as soon as the argument is kept fixed, that means that we're studying a single fixed point on that wave pattern. Of course, that fixed point could occur in different points in space, could also occur at different times. The important part is that we're just focusing on a single part of that pattern here. Now, if the argument is constant, that means that omega t minus kx is constant. And without loss of generality, and because we're lazy, of course, we're going to pick 0 for that constant. So this means that we can just write down that omega t is equal to kx. So this is a relationship between t and x that describes that fixed location that we were interested in. And here you can clearly see if t increases, then also x will increase. So as time travels on, also the wave will travel towards larger values of x. So this is a wave traveling towards the right, towards plus infinity. It's an outgoing wave. Now you might wonder what happens if we have a different time dependence. Then everything will change, of course. So here we will have minus j omega t. These two minuses inside the cosine, that will translate then to a plus here. Cosine is an even function. We'll also have a plus over here and a minus over there. So here you see that if you take a different convention, that now all of a sudden this same phasor will correspond not to an outgoing wave, but towards an incoming wave traveling towards minus infinity. So always be aware of the time convention that people use when you try to interpret results.